these people can do.
T-minus 10 seconds. T-minus 5, 4, 3, 2, 1. Ignition. We have liftoff of the S-26 Minotaur 4 space launch mission carrying 7 satellites.
Isn't it tiny? So this one is like the ocean optics one, even the one that we have in the lab is only about this big. And then they just like...
What is this thing here?
These are diffuser for, so when the sun comes in, sun is our light source and our radiation source. But these are diffusers that help to uniformly distribute the light over the sun. So basically all of
and pizza, pretty tough, and then from 6 to 7:30 they sit and do hardcore science with me. Ryan has actually come and done the math on what was the actual effect.
Okay, we're here with Giovanni. This is Eric Stackpole's office mate here at Ames Research Center. So tell us, this OREOS project, and what is your role in this program?
So I came onto the OREOS project about 2 years ago, right around its inception. I'm a mechanical engineer, and so I was a mechanical engineer for one of the payloads, for the SIVO payload, which is one of 2 payloads.
They're live here. Go ahead.
Sorry, I totally stepped on you guys. SIVO is one of 2 payloads on OREOS. It's an organics experiment, a small rotating sample carousel that contains 4 different types of complex molecules, organic materials, and we're studying how these organic materials degrade over time in the space environment. They get exposed to ultraviolet light, to radiation, to space vacuum, and we're seeing how they degrade. Because we really don't know how things operate in space over time. We don't know how the human body reacts in space. We don't know how very simple molecules.
Even though we've been having space flight longer than you've been before you were born, but there's still questions to ask of this.
Oh, absolutely. And anytime you answer a very simple question, it generates dozens of new questions that all need answering also. So that's the fun part about working in the science field, is that anytime you answer one thing, you'll just have a bunch more work to do and figure out all the more complex questions that you didn't even know existed before you've found out some basic facts.
Now you're carrying this iPhone with you and you keep looking at it. What are you, that's in your pocket right now, but you're paying attention to the spacecraft status?
I'm on, let's see, I'm on speakerphone right now. We actually, let's see, 5:44. We should be just about ready to separate from the P-pod.
So you must have been up all night long, weren't you? Or did you get some sleep last night?
I got a little bit of sleep, but I gotta say that yesterday was my bittersweet day, because this is the first time that I've worked on a mission where my designs are actually flying in space. I've worked on a couple missions before, but I'm communicating with the satellites that have already been built. And so there's a point where you start thinking about all the decisions you've made over the last couple of years and whether or not they were the right decisions in your designs and in how you've managed the project and that sort of thing. But that's why I got into this business. It's nerve-wracking, but it's also very exciting because it has to work on the first try.
Okay. So anyway, but in your role, what was the most difficult about this particular program that you worked on?
To be honest, I would say the most difficult part about this project was the funding. These nanosatellites are, by definition, supposed to be cheap, and they're supposed to do really big science on a very low budget. And our group here at NASA Ames has been very successful at producing quality science missions for a very low price tag. So the biggest challenge about these missions is to miniaturize a full science experiment to fit into a small nano satellite, and to do it on the cheap, and not to spend tens of millions of dollars, even more than that, which is how traditional satellites, that's their traditional budget. We typically fall under the cost of, this OREOS costs under $3 million, for example. So this is, it's pennies compared to other space missions, and we're expecting to deliver real science, real relevant science for a very small price tag.
Okay, now this has an amateur, a transmitter on board. I guess for a beacon. Would this have any packet information like GeneSat?
Absolutely. So just like OREOS predecessors GeneSat and PharmaSat, OREOS also has an amateur radio beacon. It operates at 437.305 megahertz, and that's a standard ham radio frequency. It transmits AX25 packets, and if you go to www.oreos.org, which is OOREOS.org, there's going to be instructions on how to decode these packets. There's instruction on when the satellite comes over, how to point your antenna at the satellite, how to listen to the beacon, and how to decode the packet, and then submit what you found to our central database and help the NASA scientists and engineers evaluate the satellite's health. The public is basically involved in our mission operations as soon as we launch.
So like PharmaSat, you're actually looking for signal reports.
Absolutely.
Like that for people that submit this in, and they got a web page. So there's a lot of interaction.
For example, with this mission, it's very relevant because we launched out of Alaska, and the first time we will be able to make contact with the satellite is 12 hours after launch. And so over the next 12 hours, we don't know if the satellite is actually on and it's alive. We think it is. We have no reason to think it's not, but we don't have confirmation. And we're relying on the amateur radio community to make contact with it before we do, if we wanted to know the satellite's health before we had a chance to communicate with it. We're expecting the radios to come on for the first time somewhere when we're around southern Africa, and then we're going to be going up along Africa through the Middle East and through northern Russia.
So tell me, what college you go to?
Santa Clara University, just down the street.
Okay, so I guess they're at Stackpole, as east of San Jose State, but both of you have actually began your engineering careers with something very exciting. So
absolutely.
Any advice for those wanting to enroll in Santa Clara University engineering program and successfully completing it?
Apply and talk to professors. And if you're already interested in a program, if you're already interested in something, let's say robotics or scientific research, any sort of physics or chemistry or biology, find a professor that's doing something similar to what you're doing, and go out and talk to them and see if you guys can generate ideas on future projects that you can work on. That would help out a lot, both with the admissions and with continued involvement in the program through your undergraduate career. So it sounds like we've deployed. And we have spacecraft authority. We've deployed. We've successfully deployed.
Okay.
Yeah. Anyways.
Okay, so Giovanni, any additionals for a wrap?
Go OREOS, and looking forward to the next 6 months of operations in space.
Okay.
Space.
Another question. The OREOS, that's a lot like the cookie. Was that by accident, or was that something?
No, this is classic NASA trying to be clever with its acronyms. So I'm sure someone out there came up with the OREOS acronym very intentionally to make it sound quite delicious.
Okay.
And it was a very delicious project. So.
All right, here with Giovanni at the Ames Exploration Center on the launch of OREOS, November 19th, 2010. Okay, thank you.
All right, no problem.